In this video, I'll briefly recap what we studied in the last class. I'll introduce the Lempel-Ziv algorithms, which are a class of universal compression algorithms for stationary and ergodic sources. In the next video, we'll see some more properties of the Lempel-Ziv algorithms and at least a sketch of the proof of the fact that they achieve the entropy rate for stationary and ergodic sources. So let's quickly recall the variable length compression problem. We have a source xn, which is the raw file that needs to be compressed. So this xn is an n length file with where each entry is taken from some alphabet script x. We assume that this is random. So far we saw that we only considered the case where xn is independent and identically distributed. So this was IID according to some distribution px, and we also assume that px is known to the encoder and decoder. So our goal is to compress this to a variable length file which we call ck, and the value of k depends on the realization. So for different instances of the raw file, we get different sizes of the compressed file. Our only constraint is that we should be able to recover xn back from ck. So there must be a decoding algorithm G corresponding to the encoding algorithm F, which ensures that G of ck is equal to xn exactly. So we want zero error, and in addition we want f to be prefix free. So the code words must all be prefix free corresponding to different. The code word corresponding to every file should not be a prefix of a code word which corresponding to any other file. And so k is the length of the compressed file, and we saw that if xn is IID, then the minimum expected length normalized by n is asymptotically equal to the entropy h of x. And we saw that this is achievable. We saw a couple of algorithms including the Shannon code, the Shannon-Fano code, and the arithmetic code and Huffman codes, and we saw that Huffman codes are actually optimal for large block lengths. Now for stationary ergodic sources, the minimum expected length normalized by n tends to this quantity, which is called the entropy rate. The entropy rate for IID sources, the entropy rate simply evaluates to the entropy itself. So our goal is basically the following. So given a file xn, we want to construct encoders and decoders which achieve the entropy rate. So far we studied the problem where px was known to both the encoder and decoder, but in practice this is not true. So we don't really have any prior knowledge of px. So what is the solution? Well, one solution is that the encoder first estimates px, so it computes the empirical PMF. Let's call this px hat. You can use this px hat to design the Huffman code maybe, and use the Huffman code to compress this. So using this, you get a compressed file. Let's call it ck, and what is stored is not just ck, but you also have to store px hat, because the decoder after all doesn't know px hat. It needs to know what distribution was used to design this Huffman code. So what the decoder does is it first reads these bits corresponding to px hat. So once it knows px hat, it can reconstruct the Huffman code and use that to decode ck to recover xn. So this is all fine, but this is not a very efficient scheme, because if you want to achieve the entropy, then you need a Huffman code for blocks of symbols, and that is not computationally very efficient. So that is one thing. And the other thing is that the Huffman code, if you do it symbol wise, then it achieves the entropy. But for a general stationary and ergodic source, the Huffman code may not be optimal. So you can indeed achieve the entropy rate if you code over sufficiently large blocks of symbols, but this is computationally not efficient. So we want a compression algorithm which works universally. So we want a universal compression algorithm which doesn't use px and still achieves the entropy rate. But in addition, we also want it to be computationally effective. So both the encoding and decoding algorithms should work in time which is polynomial, and it should be a small polynomial. Say the computational complexity. So we want the computational complexity to be roughly order n or order n log n, at most order n square, where n is the size of the file. So we want a very efficient compression algorithm. And so we'll see two such algorithms which are computationally efficient and achieve the entropy rate universally. So both these algorithms were given by the same group of people, same group. So this was devised by Abraham Lempel and Ziv. So these two gave two compression algorithms, one in 1977 and the other in 1978. So these are now called the LZ77 and the LZ78 algorithms. And the basic principle behind these two algorithms is essentially the same. And they work in the following way. So you have your source file x1, x2, x3 up to xn. So given this string of symbols, what either LZ77 or LZ78 does is that it passes this sequence into phrases. So maybe x1, x2 forms one phrase, x3 to x10 forms another phrase, and so on. So you partition these symbols into chunks of different sizes and basically encode each chunk in an efficient manner. And both these algorithms achieve the entropy rate and are universal. And in some sense, a very high level description is that what either LZ77 or LZ78 does is that it constructs a dictionary. So of commonly observed phrases. So once you have constructed such a dictionary, you can simply reference that particular phrase. So for example, certain phrases may occur very often in your file, and instead of encoding that phrase again and again using the same number of bits, all you have to do is store that particular phrase and then represent that phrase using a much smaller number of bits and use that to encode. So we'll see this in a little more detail now. So let's look at what the LZ77 algorithm does. So as I mentioned, both LZ77 and LZ78 work by parsing the source sequence into different phrases. And what is the algorithm to partition the sequence into phrases? It works in the following way. So suppose that we have already encoded up to say symbol I. So we have already partitioned. So this works in an online fashion. You start from the first symbol and you keep going on from second symbol, third symbol, fourth symbol, and so on up till n. And in an online manner, you keep partitioning it from 1 to n. So suppose that you have partitioned the source sequence into phrases up to xi. So x1 to xi has already been partitioned, and now your goal is to partition from xi plus 1 to xi, compute the next phrase. So you're basically here and you have to compute the next phrase. So the algorithm works in the following way. So given xi plus 1, you look forwards and you keep reading until you hit a point where this substring matches some substring which has been seen previously. So maybe this xi plus 1 to xi plus k has been observed somewhere over here. Then you partition it into, so you partition this part as one phrase. So the basic algorithm is the following. You find, so from xi plus 1, you look for the longest subsequence which matches some subsequence which has been seen from x1 to xi. So that's how you compute the next phrase. So that may happen. So either there is, so it could be the case that there is no matching substring, so which means that you basically see a new character which has not been observed from x1 to xi, and so this new character corresponds to the next phrase. And so let's see a quick example to see how we actually partition into phrases. So let's take the following source sequence: A B A A A A A B B A A, and so on. So you start from symbol 1. Have you seen any phrase before? No. So A. So the symbol A forms the first phrase. Now you look at the next symbol. You start from B. Have you seen B before? No, you haven't seen it before. So the next phrase is just the letter B. Now the next one is A. Have you seen A before? Yes. Have you seen AA before? No, you have not seen AA before. So the longest matching substring is simply the letter A. Now let's go here to A. Have you seen A before? You have seen A before. Have you seen the substring AA before this? No, you have not. So just the letter A forms the next substring. Now you are here. Have you seen A before? Yes, you have seen A before. Have you seen AA before? Yes, it occurs here. So you have observed AA before, so that forms the next substring. Now we are here. Have you seen B before? Yes, you have seen B before. Have you seen BA before? Yes, you have seen BA before it. You've seen it here. So the next phrase is BA. Now, have you seen C before? No, you have not seen C before, so that forms the next phrase. So have you seen B before? Yes, you have seen B before. Have you seen BB before? No, you have not seen BB before, so this forms the next phrase. And so similarly, you've seen AA before, so that forms the next phrase. So this is one way of partitioning the source sequence into phrases, and this is what the LZ77 algorithm does. But so far all we've done is we've taken this and then we've just partitioned this string into different phrases. So this is phrase 1, phrase 2, phrase 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 phrases in this sequence. So all we've done is partition the phrases. How do we encode the sequence? The encoding is the following. So what can happen? Either you have case 1 where you find the longest matching substring. So in that case you don't need to store the substring itself, but you just store the start location and the length of the match. So you find the location of the match and the length of the match, and you just need to store that. Now if it's a new character, it's a character you've never seen before, then after all you need to store the character. So you store a 0 corresponding to the start location, and then the actual character itself in its uncompressed form. So let's see. So the encoding is going to be the following way. So let's come back to this example. So A is a new character. So you store 0. A is the encoding corresponding to this phrase. Let's look at B. So B is the encoding of B is, so it's a new character, and you store B. Now let's look at A. You have seen A before. So what do you need to do? You need to store the start location and the length. The start location is the first letter in the alphabet. So it's 1. It's the first letter in the sequence. So it's 1, and the length of the match is 1. The same for this. So it's 1 1. Now let's look at this sequence AA. So the start, where is the start location? It's 1. So corresponding to this, you have so where do you have AA in the sequence so far? So this AA is what you need to store, and that is, so the start location is 3 and the length of the match is 2. So this is encoded as 3 2. And similarly BA occurs here. So the start location is 2 and the length of the match is 2. So it's 2 2, and so on. You keep partitioning this into phrases, and all you basically need to do is store each of these using some fixed length, perhaps a fixed length binary system. So all of this looks fine, but at least in the example we've seen here, it appears as if this new encoding, so we have 0A, 0B, 1 1 1 1 3 2 2 2. This somehow doesn't look like a compressed form. It looks like this requires more space than the actual raw file itself. And indeed, if the size of the file is very small, then the Lempel-Ziv algorithm performs very badly, because you need to store all of this information. The storing the start location and the length can be very inefficient if the size of the file is very small. But if the file is really large, if you look at a really large text file, then you typically have a lot more matches, and the length of each match is also going to be pretty large. So it indeed brings in some efficiency. So maybe in a later video I'll also show you how, perhaps take the example of some text file and show you how the Lempel-Ziv algorithm actually gives you gains. But hopefully this example makes the algorithm clear. So right now, again, all I have showed you is how to encode the source sequence into pairs of characters. So you store 0A, 0B. So each phrase is basically represented as a pair of either a number and a character, or a pair of numbers. 3 2 2 2, and so on. So this is how the LZ77 algorithm works. Now basically what we want to do is, so what we can do is, well, either we can store each integer using a fixed length representation, which can be extremely inefficient, or we can use a prefix free representation of the integers. So look here, our goal is to represent these integers somehow using in a very compact manner. So a priori we don't know what the size of the integer is. So in principle, now each of these, so what are we storing? We are storing the start location and the length. So these numbers are corresponding to some location and length. Now the location is basically a number which varies from 1 to n, and so is the length. And now if I want to represent a number between 1 and n, I need at least, I need log n bits to represent this. I need log n bits to represent each number, and I have a whole bunch of pairs of numbers. And we can, and if the number of phrases is actually order n, if the number of phrases is order n, then the total size of the total size which is required to store this encoding is going to be order n log n, which is extremely inefficient. We're not compressing the file, but rather blowing it up. So what we actually do is we don't use this fixed length representation. We don't use log n bits to represent the location and the length. What we instead do is use a prefix free representation of the integers. So we know that if you want to represent an integer in binary, if the integer is bounded by m, the integer that we want to encode is bounded by m, then we need log m bits to represent this. But on the other hand, if we don't have any such information, or if m is extremely large, then using log m bits is very inefficient. So one strategy is to use the following prefix representation. This is not really the best way to represent this is not really the most efficient prefix free representation of integers, but just suffices to say that any integer k, so there is a prefix free representation which represents an integer k using log k plus order log k bits. And how do you encode this? You first write log k in binary. How many bits does this require? You need log k bits, but you don't really know what k is or log k is. So what you can do is you can encode log k in binary. To encode log k in binary, you need log k bits, and roughly log k plus 1 bits perhaps, since this is C log k. And you have but you don't know what log k is. So one strategy would be to again store log k in binary. You don't know what log k is, so you can store log k in binary, which would require log k and so on, but we can just terminate at this. So you store log k, you use log k bits to represent log k in binary, but you need to of course find out what log k is. So you can store log k in unary, which means that you just store a string of log k zeros followed by a 1, which you can read. So let's take an example. So suppose I want to represent the number 18 in this prefix free fashion. Then what do I do? So what is 18 in binary? It is simply 10010, right? And how many bits does this require? So this is 5 bits. So I don't know the number 5, so the decode. So what is 5 in binary? It is 101, and so this requires 3 bits. And I can represent 3 in unary in the following way. I put 2 zeros followed by a 1. Right? So if I want to represent say 5 in unary, then I will put 4 zeros followed by a 1. Right? So the encoding of 18, a prefix free encoding of 18 would be first store 3 in unary, so 0 0 1, followed by 5 in binary, 1 0 1, and followed by the number itself, 1 0 0 1 0. So how should you understand this? Should understand this in the following way. So the first part corresponds to roughly log k in unary. The second part corresponds to the length of the representation of the actual number, which requires roughly log k bits, and this is simply k in binary. So what does the decoder do? It first starts from the very beginning, so it keeps reading till it hits the first 1, so it's 0 0 1, so this corresponds to 3, so it decides that log k is equal to 3. So then it reads the next 3 bits. The next 3 bits are 1 0 1. So what is 1 0 1? It corresponds to 5. So it decides that 5 is the length of the representation of the k. So this is log k, and using this, so the 5 corresponds to log k, and then it reads, so it has to read the next 5 bits in order to recover k. The next 5 bits is 1 0 0 1 0, and the integer representation of 1 0 0 1 0 is 18. So this is one way of finding. So let's take another example. Suppose let's take a smaller example. So suppose we want to encode say 4. Okay, so 4 in binary is going to be 1 0 0. So this requires 3 bits, and 3 in binary is simply 1 1, which requires 2 bits, and 2 in unary is going to be simply 0 1. This is unary of 2. Right? And okay, so basically, suppose we wanted to encode the pair 18 4. So suppose our goal was encode using prefix free representation, then we would basically store 0 0 1 1 0 1 1 0 0 1 0 0 1 1 1 1 0 0. So this would be the encoding of 18 4. So what does the decoder do? So the decoder first reads this in unary, so it knows that the first is some unary representation. So this is 3. So the next 3 bits correspond to so the next 3 bits correspond to log k. So it reads the next 3 bits. So reading 101, it decides that log k is actually equal to 5, and so it reads that, so the next 5 bits corresponds to k, so 1 2 3 4 5, and this corresponds to the number 18. So the next is another unary representation, so it's 0 immediately followed by a 1, so this corresponds to 2. So the next 2 bits correspond to log k, and so it reads 1 1, so 1 1 corresponds to the number 3. So the next 3 bits correspond to k, so it's 1 0 0, which is 4, so it can read 4. Okay, so hope that this part is clear. So this is a very efficient way of storing a sequence of integers, integers without any bound, or when the bound on the integer is very large. So if you have to store a sequence of integers which are all roughly of the same magnitude, then this is not a very efficient representation. But on the other hand, if there is a lot of variability, then this can be a very, very efficient representation of sequences of binary numbers. So for example, if k is very large, so suppose you want to store k1, k2 up to kn, if all of these ki's are roughly equal to m, close to m, then it would be more efficient to simply store each ki using log m bits. But on the other hand, if suppose that some of these ki's are very small and the largest ki is very, very large, so maybe most of these ki's are roughly equal to say 10 or 20, but on the other hand some of these ki's, but there are maybe 2 or 3 ki's which are close to say 1,000,000, then it's very inefficient to store it using log of 1,000,000 bits. It's more efficient to use this prefix free representation for such integers. Okay, so generating the LZ77 code consists of 3 steps. So the first step is you take the source sequence and then you partition it into phrases in this manner. The second step is you obtain this encoding of pairs of objects. So the pair can either be an integer and a character or a pair of integers. The third step is to encode this pair using in binary. So this 0 requires just 1 bit, and you can represent these characters in ASCII, and these can be represented using the prefix free encoding that we just discussed. And this prefix free representation is also useful in LZ78 as well, because the manner of encoding is quite similar. The main difference between LZ77 and LZ78 is really the way we are going to generate these phrases and how do we encode these phrases. So now that we've discussed LZ77, let's go to LZ78, and the way we obtain the LZ78 parsing of a sequence is the following. So as before, suppose that we've already parsed the sequence into phrases up to the ith character. So from I+1 we have to generate the next phrase. So in LZ77, the next phrase is the longest matching substring that was seen from 1 to I. So it was seen previously. In LZ78, you look for the shortest phrase which does not match any previous phrase. So LZ77, it was the longest phrase that matches a previous substring, not a phrase but a substring. And here we are looking for the shortest phrase from I plus 1, starting from I plus 1, which does not match any previous phrase. So in other words, the shortest phrase that does not match any previous phrase is actually going to be the longest matching phrase plus some other character which is not included in this phrase. So again, let's take an example. So suppose we have this A B A A A C B C B B B A A. So we start from the beginning. We have not seen anything so far. So A corresponds to the first phrase is simply the letter A. Now the next letter. Have we seen B before? No, we have not seen B before. Therefore, the next phrase is B. Now let's look at A. Is the letter A a phrase? Yes, it is a phrase. It occurs here. Is the letter AA a phrase? No, it is not a phrase. So AA is going to be the shortest non-matching phrase that has been seen so far. So AA is going to be the next phrase. So now let's see. Is A a phrase which has been seen previously? Yes, A is indeed a phrase. Is AC a phrase that has been seen previously? No, it is not the phrase. So AC is the shortest non-matching phrase. So AC is going to be the next phrase. Let's see B. Is B a phrase, a previous phrase? Yes, it is a previously seen phrase. So B, but is B a phrase that has been seen so far? No, it has not been seen so far. So BB is the next phrase. Now let's look at another interesting example. So is B a phrase that has been seen so far? Yes, indeed, we have seen B over here. It is a phrase. Is BA a phrase that has been seen so far? No, it is not. So while BA is a substring that has been seen previously, BA is not a phrase that has been seen previously. So BA has not been a phrase. So BA is the shortest non-matching phrase. And then you keep proceeding. So, okay. So how do we encode the LZ78 parsing? So we store each phrase in the following way. It is the location or the index of the matching phrase. So we saw that each phrase consists of so it's obtained by the longest matching phrase seen previously plus some character. So the way we encode this is we store the location or index of the matching phrase and then the character in the uncompressed form. So in this example, A is a phrase that has not been seen previously. So 0 is a location of the matching phrase and a character A. B is again a new character, so we store 0B. So this is phrase 1, phrase 2, phrase 3, phrase 4, 5, 6, so on. So let's look at the third phrase, AA. So AA has a match, so the match is in the first phrase and the new character is A. Let's look at AC. So A matched with the first phrase, so it's 1 and the new character is C. Let's look at BB. BB, there was a match, so B corresponded to this B matches with this B and the new character is B, so it's 2B. Similarly, BA is 2A and so on. So this gives you the encoding, but of course to actually store on a file, the compressed file is obtained by encoding each of these in binary. And once again we can use this prefix free encoding of integers to actually store this. Now let's take another example which illustrates the difference between LZ77 and LZ78. Now if you think about it carefully, what you're doing is you're first partitioning the sequence into phrases. You're encoding each phrase as a pair of objects, and then you're encoding and then you're storing each object in binary using some method, using the prefix representation, for example. Now if you want the file to be really compressed, to be well compressed, if the compressed file size has to be very small, then the number of phrases should be very small. So if each phrase is very big, then you can represent the compressed file using a fewer number of bits. So it's good for us if the number of phrases is very small. And when is the number of phrases very small? It's very small when there is a lot of repetition. So if these phrases match with many other phrases previously, then it will be good for us. And so in that sense, what is the easiest file to compress? The easiest file is one where there's just one character which is continuously repeated throughout. So So for AAA, how would we generate the Lempel-Ziv LZ77 parsing? So you start with A. You look for the longest matching substring, so it would be A. So A has been seen previously. So now you are here. Have you seen A before? Yes. Have you seen AA before? Yes, you have seen AA before. So the next phrase would be AA. So now you are here. Have you seen A before? Yes. Have you seen AA before? Yes, you have AA over here, you have AA over here. Have you seen AAA before? Yes, you have AAA. You have AAAA before? Yes, you have seen AAAA before. And so on. On the other hand, let's see what would happen for LZ78. LZ78, have you seen, so the first phrase is the following. Have you seen A before? Yes, so A is a previously seen phrase. So the shortest non-matching phrase is AA. Now we start from here. Is A a phrase? Yes. Is AA a phrase? Yes, it is a phrase. So the shortest non-matching phrase is AAA. Now, is A a phrase? Yes. Is AAA a phrase? Yes, it is. It is this phrase. Is AAAA a phrase that has been seen previously? No. So the shortest non-matching phrase would be AAAA. So from this example, we can see that LZ77 and LZ78 give different parsings of the source sequence. So we'll stop here for this video. In the next video, we'll see some more properties of the Lempel-Ziv algorithms and maybe a sketch of the proof of how they actually achieve the entropy universally. So perhaps before I end, maybe I'd like to make one comment in passing that if you look at the LZ77 and LZ78 algorithms, this is not, well, we haven't used it. It's very different from the compression algorithms that we've seen so far. Basically, what we have done is we took a string and then parsed it into phrases and encoded each phrase. So this is an online. So in some sense, this is an online algorithm that you can start from character 1 and then keep moving till character n, and essentially with two parsings of the entire sequence and a little bit of memory, you can encode. You can find the Lempel-Ziv encoding of a sequence. So this algorithm is extremely efficient. We did not make use of the source distribution, so it is in a sense universal. What is perhaps not clear is how this achieves the entropy. In fact, from the looks of it, you wouldn't even expect this algorithm to actually achieve compression. I mean, if you look from the tiny examples that we've seen so far, it appears as if the size of the compressed file must be greater than the size of the raw file. But in fact, that is not the case. That is not the case provided that the size of the file is sufficiently large. And hopefully some of that will be clarified in the next video.